Welcome to our discussion on compounding. Compounding can be a beautiful thing or it can be the worst thing in the world. It just depends on if you're compounding interest on money you own versus money you owe, because compounding can make things grow very, very quickly. Some definitions. The principal is just the amount of money, right? It can be the starting principal that you borrow, or it can be the starting principal that you deposit into an account that you're hoping to, use to earn interest. Simple interest, it really doesn't happen anymore in the real world. It's more of a teaching tool or something that helps you understand how compound interest works. Very few places ever deal with simple interest. It's the idea that you're just going to pay the same percentage every year based on the original amount, rather than each year interest is now being compounded, being computed on the new amount each year. And that's where compound interest comes into play, where interest is built on top of the interest earned from the previous year. So let's take a look at some examples to see what we mean between the two. So since banks always pay compound interest, bonds usually pay simple interest. So suppose you invest $1,000 into a savings bond that pays simple interest of 10% per year. How much total interest will you receive in 5 years? If the bond paid compound interest, would you receive more or less total interest? Well, if we're getting simple interest, then that means we're getting $10,000 a year on that original principal. So after 1 year, we get 10% of 1,000 or $100, and we now have $1,100 in our account. At the end of that second year, even though we have $1,100, we still only get 10% of the original amount. And therefore, we just get another $100, and then we have $1,200. And it does that 5 times. Obviously, we get $100 each time. We get $500 total dollars, and we would have $1,500 when we're done, right? Okay, so that's simple interest. That's how it works. That every year you're still just simply getting interest on the original amount, the original starting principal. Compound interest, however, you would receive more than $500, and it's pretty easy to see that because in that second year, instead of just getting the $100 because you were getting 10% of the original $1,000, you're now getting 10% of what you have after that first year, and you now have $1,100, so you get 10% of that, which is $110. So you see you get an extra $10 right then and there. You add that, and then you have $1,210. Then when you do the 10% on the third year, that's going to give you $121. And it's just going to keep growing like that. So at the end of 5 years, you're going to have more. Not a lot more, but probably maybe $50 more, probably closer to 40. But that's because A, you started with a small amount, and B, it was only for 5 years. But it's still, $40 is nothing to snub your nose at, as they might say. So here is our first formula, and I'm going to tell you right now, ignore it. The reason why is because we're going to see another formula here very shortly that does everything this formula does and then some. So why kind of memorize two formulas when you can just memorize one formula that does the job of two? But let's go through this just so you understand the bits and pieces, and then you'll see the new formula that's a slightly different variation. You'll see how it works, and you'll see how it's easier to just use that one. Okay, A, they call your accumulated balance after, Y years. It just means a lot of people just call it the amount that's in the account after so much time. P is your principal, your starting principal. APR is just your annual percentage rate, always written as a decimal, which means if you're getting 5% interest, right, you would write your APR in terms of a decimal, and it would be 0.05, because that's 5%, right? And if it was, let's say, 3.5%, it would be 0.035, right? So you always have to list it as a decimal. And then, of course, Y. Sometimes the formula will have T for time instead of Y for years, because you don't have to do this in years. You could do compound interest for 6 months, but the time is always in years. So if you were going to do it for 6 months, you would put 0.5 up there because that's half of a year. So that's why some formulas use Y for years, to remind you that your unit of measure is years. Okay, let's look at an example. So you invest $100 in two accounts that each pay an interest rate of 10%, which is pretty darn good. One pays simple interest, the other pays compound interest. Make a table to show the growth of each over a 5-year period. Well, we already talked about what would happen with simple interest. You just keep getting $10 a year, right, for 5 years, and you end up getting $50 in interest, or $150 total. If you use the compound interest formula, without even using the formula, we can just do the math because 10% is so easy. We get $10 the first year, but then now the second year we're doing 10% of that new $110, which gives us 11, which brings us up to 121. Then we do 10% of that, which is $12.10, which brings us up to 133.10, and you can see the pattern, 146, all the way up to 161.05. So we made a whopping $11.05 more in 5 years. And you think, well, what's the point for only $11? Well, a couple things to keep in mind. A, we only had $100. So we made $11 more on $100, which means we made 11% more on $100. That's pretty good, right? You make 11% more in 5 years with compound interest. So now instead of $100, think of $100,000. Now you make $11,000 more. That's how interest can really rack up both good and bad, because if this was a debt, then you're, in debt by that much more. Okay, so we can actually just go straight to the end, right? We don't have to do all those steps and figure out how much we got each year by just using the formula. Plug in our starting principal of $100. Our APR was 10%, so that's 0.1. Our years was 5. The first thing we do is inside the parentheses, so we add those together and make that 1.1. Then we do the power, which gives us 1.6105. Then we do the multiplication, and there's our 161.05, which is exactly what we had on that last line. Okay, now we can look at quarterly compounding versus just, yearly compounding. Quarterly compounding just means you take your compounding, and instead of assessing your interest just once at the end of the year, you do it every, X amount of time. If it's quarterly compounding, then you do it 4 times a year, which means you do it every 3 months. You can have monthly compounding where it's done every month. You can have daily compounding where it's done every day. You can have semi-annually, right? You can just cut the year up into whatever measurement you want. You can even compound every second of every day if you want. And then eventually we'll see what we do. What happens in most of life is continuous compounding, where in theory it's compounding every nanosecond of every second of every day. And there's actually a formula to do that. All right, so here's a table just showing you what happens, that if you were to compound 8% per year, instead of doing it once, right, you cut it into 1/4 of it, and you get 1/4 of it 4 times a year. So if you actually did the compounding just once at the end of the year, instead of taking 1/4 of it 4 times, right, every 3 months, then you would basically just get 8% of $1,000, and that's $80. You can do that very simply in your head or in your calculator, and you can see here that we made $82.43. So you make an extra $2.43. Again, you're thinking, big deal, but again, remember that it's only $1,000 and it's only 1 year. Okay, so this idea of taking our interest rate, right, we took the $8 and we split it up into 4 equal parts. We divided that 8% by the number of compoundings. And since we were doing quarterly compoundings, we divided it by the number of compoundings per year, right? So even if we did this for 12 years, we would still just divide it by 4, because it was 4 compoundings each year. You wouldn't do, okay, 4 times 12 is 48 and cut it up into 48 pieces. You would just cut it up into 4, so you get 2% each. That's what brings us to our new formula, this one. And you'll notice that the only difference between this and the old formula, right, the first one that we saw, is that our APR is now being divided by n, because if we're compounding n times per year, we have to take that total yearly, right, annual yearly percent rate, and cut it up into equal parts. And then, because we're compounding it multiple times per year, our number of compounds is now y for years times n, times how many times it's compounded each year. So that's the only difference. Very easy to kind of remember this one instead of the other one. And now we can do both situations because the previous formula was only supposed to be used when we were compounding once per year. Well, if we're compounding once per year, then what does n equal? 1. And when n equals 1, we get the exact same formula, right? APR divided by 1 is just APR, and we end up getting A equals P times 1 plus, I'm just going to say R for interest rate, to the Y, because n equals 1 in both of those places for 1 year, right? So this is for yearly compounding. But we don't need this formula because this formula is the same thing if you just put in, well, for yearly, our number of compounds per year is 1. Okay, so now instead of 2 formulas, we just have 1. Here's an example. You put 5,000 in a bank, pays an APR of 3%, compound your interest monthly. How much money will you have after 5 years? Compare this amount to the amount you'd have if interest were paid only once per year. Okay, so we know our starting principal P is 5,000. The interest rate is 0.03 as a decimal. Because we're doing monthly compoundings, our N is 12 and our Y is 5. We've identified all the bits and pieces. We throw it into our formula, bing, bang, boom, we do the math, and there's our answer, 5,808 and 8 cents. Now, if we were doing interest paid only once per year, N would all of a sudden become 1, and then our formula that we care about becomes the old formula that we're just going to ignore because we could still just use the original one and let this equal 1, right? And that equal 1. But in any case, if you put those numbers, the same numbers in, right, but only now n equals 1, you only get 57.9637. So not a huge difference. Again, not a lot of money, a pretty small percentage rate, and you might think 12 years is a long time, but in money sense, especially with small amounts, that's not a lot. But again, it's still worth knowing that the more you compound, the more money you get. It might not be a lot, but you're making, what is that, about $12 more? So it is worthwhile to compound as frequently as possible if it's your money. And if it's money you owe, then of course you want to be compounded as infrequently as possible. But like I said, everybody does continuous compounding, which is the absolute max that there is. Okay, another definition, the annual percentage yield, or APY, which is sometimes just called the effective yield or just sometimes the yield. This represents the actual percent that you pay after a year. It's basically saying, okay, if you're paying 3% and it's being compounded monthly, then at the end of the year, what percentage did you actually earn? It won't be 3% because we just saw from our previous example that because we were compounding monthly, we ended up making more than if we had compounded just yearly. So there's always kind of that equivalent that had you just done it once a year instead of every month or every 4 months or every week or every day, what would be the difference? And then that would be our APR. Or sorry, that would be our APY. We call it the yield. It's how much you actually make. So when credit cards tell you that your annual percentage rate is only 19%, well, that's 19% that's being compounded continuously. And when you compound something continuously, it grows a lot faster than if you compound it just once at the year. And so a 19% APR actually feels like, right, it has a yield at the end of the year. You may have paid as much as like 20 or 21% because of that continuous compounding. And we'll do a couple examples so you can see how that can actually work. So here's the difference between the two, right? Your APR is your annual percent rate, APY annual percent yield. The two equal each other only if things are being compounded annually, and otherwise, if you're compounding more than once a year, the APY is always bigger. Here's an example with 8%. So you can see that if you compound something at 8% once a year, then it's 8%. But if you do it quarterly, at the end of the year, you actually paid 8.24%. So that would be the same as if you just compounded once at 8.2432160, right? You would end up having the same amount of money than if you compounded at 8% 4 times. Once you go to monthly, it almost becomes 8.3. When you go to daily, it's a little bit more. If you did it 500 times a year, which is almost twice a day, and then you can see it goes up 1,000, 10,000. When you get up to a million times, 10 million, get up into the billions, you can see it starts to level off, right? The differences aren't very much. It's still 8.328 for all of those. And then all that happens, it goes from 0, 1 to like 3, 6, then 6, 7, then 7, 0, and then those are all 7 zeros. In fact, they all have 706. And all that's happening is that last little tiny number way down here, this really, really infinitesimally small part of this is just barely getting bigger. It really starts to level off. And mathematicians a very long time ago noticed this pattern and they saw it. It ends up looking kind of like a logarithmic curve or an inverse exponential curve. And we saw that there is actually a maximum, that if you let the number of compoundings go to infinity, that it's actually going to reach a maximum level. And in this case, that maximum level is 8.3287068. It kind of goes on from there, but we round off. And what it ends up being is it ends up being that special number E. If you don't know what E is, it's a special irrational number. It's just like pi, where it's an actual number, but it's not a whole number, and it's not a nice fraction. 1/2 can be 0.5. 1/3 can be written as 0.3 repeating. Pi, 3.14159, blah, 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 blah. It doesn't terminate. It never repeats. It's called an irrational number. Well, E is the same thing. It's another irrational number. It's just 2.71828 and then a bunch of junk after that. And it's the number that gives us that maximum, that blue line that the compoundings reach as your compoundings per year go to infinity. And that's that idea of continuous compounding, that it's every micro nanosecond of every day. And then we get this lovely formula, which you can see is very similar to our previous formula. It still has the A, it still has the P. It still has an APR and it still has a Y in there. It's just slightly different. And I'll write the other one up here so you remember what it was. It was A equals P times 1 plus APR over N raised to the N Y. So all that's changed is instead of compounding NY, right, we've got Y. And instead of P times this stuff, we have P times E raised to this stuff. So this whole piece here is basically what happens to this piece here when n goes to infinity. As n goes to infinity, there's some mathematical properties I can show you with algebra and things like that. And what happens is you end up getting E, and this is what you get. Okay, so some people, again, instead of APR, a lot of people just write it as R for rate, for interest rate. And then this formula becomes P E to the R Y, right? And so they think about Perry to remind themselves. A Perry is one way to memorize the formula. Our last example. So we're going to go back to putting that $100 in an account at 8%, and now we're going to do continuous compounding. You'll remember that up here, 8%, as it compounded more and more and more, got to 8.328. Here, we're going to do continuous compounding. We're going to do it for 10 years, plug everything into the formula, and you can see that at the end of 10 years, our $100 has become $222.55. Remember, the answer we get is A, the amount in our account. It's not interest, it's the actual amount in our account. So in 10 years, our money has more than doubled at 8% because of continuous compounding, which is a pretty great thing if you're saving money and a pretty horrible thing if you owe money. Okay, that's it for continuous compounding.